Probably just made some really annoying noise for the headphone people. Sorry about that. All right. Let us begin with a word of prayer. Dearly Father, we thank you for this day. I thank you for these students. Just ask you to bless this class today, Lord. In your name I pray. Amen. Okay, guys. So we are now to the point in the story where we can solve pretty much any problem of the form, dx. Oops. If we have a problem of the form dr dt equals to ar, we can solve it. So a big picture, here's a sketch of the method. One, you find your eigenvectors and or generalized eigenvectors. Step 2, you use data in 1 to construct either eigensolutions or generalized eigenvector solutions via the magic formula that I wrote last class, right? The magic formula was e to the ta equals to e to the t lambda times I plus t times a minus lambda I plus t squared over 2 a minus lambda I squared, and so forth and so on. And the thing we noticed is that if you hit the magic formula, or rather if you operate on a generalized eigenvector with the magic formula, provided we set the generalized eigenvectors up in chains, then we get really nice formulas, which give us concrete expressions for the solutions to the differential equation dr dt equals to ar. Of course, on top of the construction in 2 is we still need to take anything we get that's complex and take the real and imaginary parts of those to get honest to goodness real solutions, right? So there's still that wrinkle even in the generalized case. And then, so 3 is, construct R equals to C1 C1 R1 plus C2 R2 plus Cn Rn from construct from R1 R2 Rn found in 2 that. Now step 4, which is not necessarily, this is the general solution, right? So if we're just interested in solving, great, it's done. But there's other connected questions, fun add-on questions. You could be given, if you're given that R of T naught is equal to R naught. So suppose you're given an initial data, right? This is an nth order problem, so you need n separate scalar data conditions. But if you fix one vector, that's n conditions at once, right? And so if I had an initial vector R naught, then can select particular C1, C2, Cn to solve the initial value problem, right? What are other things we could do? Another thing we could do is we could construct the fundamental solution matrix. How would we do that? I usually use a big X for it. What you do is you just put the solutions like that. So that would be a fundamental solution matrix. The fundamental solution matrix is a matrix of functions. You could, by the way, in retrospect, have written the answer over here as this big X times a constant vector, where the constant vector is, you know, C1, C2, Cn, right? What's the other fundamental solution matrix we had? What do we prove? Last time we argued that the matrix exponential gave us a fundamental solution, right? So the matrix exponential can try to relate x to e to the ta, right? Those don't, in fact, I don't think those would be the same. They would very rarely be the same thing, right? So both this x that I'm talking about and e to the ta, these are both matrices where every column is a solution, right? And they're invertible. So you can argue that these two matrices have to be related. Let's see how. So check this out. If we say, well, how about this? Column, the jth column in the matrix exponential is a solution, right? It's a solution for dr dt equals to ar, right? But if x is the fundamental solution matrix, that means that we can write any solution, right? Any solution whatsoever as a linear combination of the columns of x. So this is equal to, you know, C1R1 plus plus CNRN for appropriate choices, you know, for appropriately chosen constants. But again, I think it's better to look at that as a matrix column multiplication. This is really just, you know, the fundamental solution matrix times C. So check it out. We can do this for each j, right? Maybe I should call this constant, like, you know, the jth c sub j, just to be, because it has a dependence on the jth column, right? So okay, fine. So I better label, I better add a j to these, right? Let's say 1j cnj. So c1j, c2j, cnj. Because I need constants, I need different set of constants for each column, right? And each column in the matrix exponential. But then what we've got is we've got column 1 of the matrix exponential is equal to x times this constant vector c1. Column 2 in the matrix exponential is equal to x times column vector 2, and so forth and so on down the line until we get to the nth column. But what we want to do is look at these all at the same time using the column by column matrix multiplication. So what would e to the ta be? Well, it's column 1 of e to the ta glued together with column 2 of e to the ta, and so forth and so on until we get to the nth column of e to the ta. Now, as I've just argued, that's equal to x times c1, x times c2, x times cn. But what did we learn about matrix multiplication? If we've got the same matrix multiplying each column, right? then by the column matrix multiplication rule, I can factor the x out. And I just have x times what matrix? Times a matrix of constants, yeah? So this is a theorem. There exists a constant matrix, C, such that x times C is equal to the matrix exponential. That's what this calculation shows you. In fact, did this have anything to do with the matrix exponential? This argument I just gave, did we really use any property of the matrix exponential at all here? We've not even used invertibility of the matrix exponential yet. All I used was that each column in the matrix exponential is a solution, right? And as such, it can be written as a linear combination of the solutions in the fundamental solution set, which glues together to form X. So in fact, if you think about it, this would still be true if we replace the matrix exponential with just any other solution matrix. What's a solution matrix? So if X and Y are both fundamental solution matrices, then there exists C invertible, in fact, such that X times C is equal to Y. Now, that I haven't quite proved yet, but that's pretty easy to prove. What's the determinant of a product? See, the determinant of X times the determinant of C is equal to the determinant of Y. So the fact that XC is equal to Y is given by the fact that we're assuming X is a fundamental solution matrix, right? So if Y is also a solution matrix, and it's invertible, in other words, it's a fundamental solution matrix, then it forces this constant matrix to also be invertible because the determinant of the product is product of the determinants. An invertible matrix have this non-zero, right? This is non-zero. So that forces the constant matrix to also be invertible. The same is true, in fact, for my bubbled theorem, that C actually has to be not just a constant matrix, but an invertible constant matrix. All right? All right, great. So you may or may not care about what I'm telling you right now, but there is a really nice theory for fundamental solution matrices. Right? Any two of them for a given system are just related by multiplication by a fixed invertible matrix for a given pair. If you had different pairs of invertible, if you had different fundamental matrices, they would be related by different constant invertible matrices, right? So what does this matter to us? Well, this actually gives us a way to calculate the matrix exponential directly from the solution matrix if we found it. So let's look at it. Let me show you an example of that. So what do you mean? How is that the case? Well, check this out. This holds for all t, right? So what's the t? So to write that out more explicitly, this is x of time t times the constant matrix C is equal to e to the ta, just making the time dependence explicit. So if you wanted to, understand what C is, what's a nice choice of t to get your paws on what C is? 0. Yes, put t equal to 0. Thank you. So that would say that x of 0 times C is equal to e to the 0, which is, as we discussed last time, the identity matrix. So therefore, this constant matrix I'm talking about in these theorems is not just any old constant matrix. In fact, it's equal to the solution matrix X evaluated at 0, the inverse of that. Which for a 2 by 2 matrix is something we can just straight up calculate with like without a lot of work, right? The 2 by 2 matrix inverse formula is known to us. Okay, so in fact, let's write down the improved version. What's the improved version of the theorem we just discovered? We have a theorem, e to the ta equals to x of t, right, times x inverse of 0. So if you find a solution matrix, you can multiply it by its inverse evaluated at 0, and that's going to be the matrix exponential. I don't know about you, but I think that's probably easier than calculating the series directly, unless the matrix is particularly nice. I think I have given you a problem in the quiz where it's actually kind of nice to calculate the thing directly. Here, let me just flesh this out for a specific example. Let's see here. Suppose we're looking at dr dt equals ar with a equal to, can you guys remind me one we've already worked? I don't want to do another one from scratch here. I mean, I guess we could. Here, I'll do one from scratch. Why not? It's probably good for you to see another. What if we had, I don't know, 3, 4, 4, 3. I know I can work this one out and it won't be too ugly. So what's the determinant? So what I got to do, guys, my goal here is to derive the fundamental solution matrix and then calculate the matrix exponential. That's what I'm trying to do right now. Okay. So this is beyond just finding the solution. It's something a little bit more past just finding the solution. Okay, so 3 minus lambda, 4, 4, 3 minus lambda. And that's lambda minus 3, quantity squared, minus 16. So we get lambda minus 3 minus 4 times lambda minus 3 plus 4. Or, like you guys probably have factored in a less weird way, lambda minus 7 times lambda plus 1. So we're looking for eigenvectors with eigenvalues 7 and minus 1 respectively. I'll start with the minus 1. Lambda 1 equals to minus 1. I'm looking to find something in the null space of, well, a plus I. In other words, I'm trying to find a non-zero solution at the moment, an eigenvector to this equation. Let's see here. So what's, oh, that's 4, 4, 4, 4, 4, right? 4. Sorry, I'm an idiot. UV. So what was the trick I told you guys last time? Just think about like finding a perpendicular vector. What's a perpendicular vector? To 1, 1. You know it, Taylor. 1, negative 1. That's right. All right. Very good. And if we look at lambda 2 equal to 7, we're looking for a minus 7i times u2, which, by the way, is, well, minus 4, 4, 4, minus 4. So Ian, what's my eigenvector? Thank you, Taylor. All right. But it's good. It's good. It's good. should get her number so you could like text. It'd be less. So you like. I failed to see the humor in this story. Okay, that's a lie. That's a lie. Anyway, so those are your eigenvectors, right? Therefore, my first solution, R1, oh man, this marker is just trash. My first solution, R1, what's that? Well, it's not dead. It's like it's just got. Well, I know. I just stupid things are. I have a suspicion if you do this enough, it probably works. Whoa! Oops.
Oh my God! It works.
Yeah, I have a. Yeah, well, it's, yeah. Have like a, no, it's just the marker. I think I'm going to be marked for the rest of the day. You'll think I've voted or something. So you're, oh, what are you doing? You know, like some of those countries, you mark your finger once you voted, so you can't go vote again. You know, we should start doing that. Yeah, but you can take the sticker off. Well, do we? Let's see here. So R1, sometimes. R1 is e to the minus t, 1 minus 1, and R2, these are eigensolutions, right? E to the 7t, 1, 1. Had it. You're dead to me. All right, so this, look at that. That's what red's supposed to look like, sort of. E to the minus t minus e to the minus t, right? And this one is just e to the 7t, e to the 7t. So these are my fundamental solutions, right? We can put them together to make the fundamental solution matrix, which I called X. What is that then? X of t, of course, is equal to, let's see here, e to the minus t minus e to the minus t, e to the 7t, and e to the 7t. There you go. This is the fundamental solution matrix. Now, I said we could write down the general solution. What's the general solution look like? It's C1R1 plus C2R2, right? So we could solve it. But what I want to do is I want to find the matrix exponential using the theorem I just worked through, okay? So to calculate e to the TA, consider what's the inverse matrix at time t. So let me tell you guys this. I know you all have not had linear algebra. Some of you have, some of you haven't. I think I've said this formula before in here, but let me say it again. The 2 by 2 matrix inverse formula is this. If you got A, B, C, D, then the inverse of that is 1 over AD minus BC. You flip the diagonals, and you put minuses on the off diagonal. So this is a known formula for the inverse of a 2 by 2 matrix. It works whether A, B, C, D are numbers or whether they're functions. This formula still makes sense over much more exotic contexts than this, but all right, so my A is e to the minus t, my D is e to the 7t. So when you look at that, we've got 1 over, okay, e to the minus t, e to the 7t, plus e to the 7t, e to the minus t. Minus and minus give me a plus, right? I flip the d and the a, which gives me e to the 7t minus e to the 7t, e to the minus t because minus minus is plus, and e to the minus t. All right, so that is e to the minus 6t over 2. And then we got e to the 7t minus e to the 7t, e to the minus t, e to the minus t. I just combined these to get a 2e to the 6t, and then brought the e to the 6t upstairs, got an e to the minus 6t, right? Now, we can multiply this through. I'm going to leave the half out front, but what we got is we've got 1/2 e to the t minus e to the t, e to the minus 7t, and finally e to the minus 7t. So there you go. That is the inverse of the fundamental solution matrix as a function of time t. Now what do I need to do to find, yep, what have I done?
Just wouldn't it be a lot easier to do it in the other order? Like find x0 first and then the inverse of that?
That would be fine. You could also do that. But the reason I'm doing this is we need the symbolic inverse for another thing later.
Okay.
I have my pedagogical reasons, but your reasons of lazier calculation I accept. So what Taylor is saying is, why don't you just plug in 0? That gives you a numerical matrix and invert it. You're going to get to the same thing. So what Taylor is exploiting is the following fact. X inverse at time 0 is equal to x of time 0 inverse. So here I'm talking about finding the inverse as a function of time and evaluating at time 0. Over here I'm saying plug in time 0 first and then invert. It's true that these are equal, so you could go either way, absolutely. We will both agree that the x inverse of 0 is equal to, well, 1/2 minus 1/2. Let me leave the half out front. I'm sorry, guys. It's equal to 1/2 times 1 minus 1, 1, 1. Right? And so, e to the ta is what? E to the ta is equal to, if I believe my theorem, x of t, which was what? E to the minus t, e to the 7t, minus e to the minus t, e to the 7t. And then I'm supposed to multiply that by 1 minus 1, 1, 1. What am I going to do with a half? A half is a constant. We can pull a constant inside a matrix multiplication out to the front. So just pull the half out front and keep it out here. Don't let it get in the way. Now we got to multiply these matrices. So let's do that. So I multiply this column times that row to give me what I'll put under red right here. We get e to the minus t plus e to the 7t in the 1, 1 spot. Then we take the first column and we take the dot product with the second row. All right, that gives me the next entry. So we do this one, dot product with that one, and that will give me this. I'm going to leave the half out front, guys. So the green dot the green gives me minus e to the minus t plus e to the 7t. Next up, we'll take the second column and take the dot product with the first row. That will give me minus e to the minus t plus e to the 7t. And then finally, we'll take the second column and dot with the second row to obtain the 2, 2 position in the product. That's going to give us minus minus gives me plus, so I get e to the minus t plus e to the 7t. And there you go. That is the matrix exponential. All right. And we didn't have to calculate an infinite series of matrices, as it turns out, right? Okay. Now, again, our main goal in this course is to solve differential equations, right? So why am I doing this? Because I think that this calculation has much goodness in it for you. We're calculating eigenvectors, we're calculating eigenvalues, we're looking at matrix multiplication of 2 by 2 matrices, we're inverting 2 by 2 matrices, we're thinking about matrices of functions. There's all kinds of good steps in this example, despite the fact that from a larger perspective, it's just math, right? Just math. Oh, what an offensive phrase is that. All right, let's see here. So, let's move along here. What's up next is the non-homogeneous problem. So we probably spent an equal amount of time, or possibly more, depending on the semester that you're looking at, on the non-homogeneous problem versus the homogeneous problem for the nth order problem. That is not the case here. The non-homogeneous problem is almost an afterthought for this part of the course because it's pretty simple. And also a real pain for me to test because it goes back to the thing that you guys do bad on in test 1, which is what? Calculus. Integral calculus, right? Many of you have forgotten how to integrate basic stuff. It's unfortunate but true. So for me to really test non-homogeneous problems is for me to, pour salt in that wound, and I just don't see the point in it. So I can test the non-homogeneous problem without actually being too explicit for the most part. It's a smaller part of what we're doing, not just because I'm trying to save you from, the suffering, because I do want you to fix your calculus, because the final is comprehensive, and we will come back to that integration that you didn't know. It's going to happen. Yeah. But here's the non-homogeneous problem. So we're trying to solve dr dt equals to ar plus f. So this is a given, non-zero, pretty nice function. And I'll say nice just to be a little bit vague, but we're probably assuming it's at least piecewise continuous. All right, so you could integrate it in a natural way, all right? And so also we assume that A is an element of Rn by n. In other words, we're looking at the constant coefficient problem. You might wonder, I wonder, the derivation I'm about to do we need to assume it's constant coefficient? Let's just leave that open for debate, whether or not we need to limit the derivation I'm about to do just to constant coefficients. I will say this. Only in the case of constant coefficients can we actually calculate the fundamental solution matrix. All right. If I was to ask you to find the fundamental solution matrix for something like, I don't know, x, y prime equal to t t squared e to the t sine t xy. This problem's not even on our radar. All right, that's a variable coefficient problem. That problem frightens me with respect to this course. Like I would not assign that unless I had messed around with it for a while beforehand. I mean, these kinds of problems are tough. So the difference between that kind of problem and the ones we've been working is, like, that kind of problem, people should pay you money to solve, right? The ones we're solving, they're harmless. That one, ugh. All right. We do learn some techniques a little bit later with Laplace transforms that might help us with that. But anyway, so when the matrix of coefficients is constant, though, we have a method to find the solution, right? So there exists a fundamental solution matrix X such that two things hold, right? Dx dt is equal to ax, and the determinant of x is not equal to 0, aka x inverse exists. And it's going to exist for all time in the domain of definition for the differential equation. Actually, though, to be honest with you guys, the theory of linear differential equations says that such an x exists even for non-constant coefficient problems. Probably given we do need to assume some things about the coefficient functions being reasonable and so forth, but the existence of the fundamental solution matrix is known outside of the problem we've been focusing on the last couple of classes, okay? All right, enough about what we can't do but can think about. Great. So what would a good way to guess a solution be, maybe? So here's what I propose. I propose that we think about the particular solution, Rp equal to, I don't know, how about x times a vector of unknown functions. So this is variation of parameters for systems. The parameters here are v. Perhaps that's a general enough guess to solve the problem. Let's see if it works. How do we see if it works or not? What do we do? Every time we make a guess in this course, and then educated guess, hopefully, and then try to see whether or not that serves to solve the differential equation, we do what? We take it and we plug it in, right? And then see what that puts on us. Whether or not we can, work our way out of that. Well, I haven't really showed you many guesses that don't work, have I? I mean, we could do that, right? We could spend 70% of time doing stuff that didn't work just to... I mean, we could do that. Some semesters I do that. Not on purpose, though. See here, so maybe not 75%. DRP, we want this to equal to what? We would like for that to be equal to A RP plus F, right? This is necessary condition for RP to solve star, right? The problem at hand. All right. So then what? Well, now we put in the guess, right? What was the guess? The guess was that RP can be written as the fundamental solution matrix times V, which we don't know. Okay, so then what's the derivative? So what's the derivative of a matrix of functions times an unknown column vector of functions? What's the calculus here? There is a product rule, right? Because we're looking at products of functions of time, one matrix, one column. And the product rule is the most natural thing that you could think of. It's exactly dx dt times v plus x times dv dt. The ordering matters here because you can talk about a matrix times a column vector, but you really shouldn't talk about a column vector times a matrix, right? Not unless the matrix is a row or something. But anyway, that's the product rule. And what do we know about x, though? It's a solution matrix, right? So what's this equal to? That's ax, we're assuming, right? So what do we got here? We have drp dt is equal to ax v, right? Plus x dv dt. And what's this supposed to be equal to? Remember? We're trying to make it equal to that. So what's that? That's a times what? xv, right? Plus f. So you see what happens. Yeah? Right? Here we go. Cancel. And so what do we have? We have dv dt, x times dv dt equals to f. We're trying to find the little v, right? That's our parameter. Our goal is to find a formula for that will make it a solution. We're almost there. How do you solve for dv dt? We know x inverse exists, right? So multiply by x inverse, and get that dv dt is equal to x times f. And then, oh, yeah, wow, you guys are fast. All right, you guys are following along too much. I'm going to speed up. All right, so, no. So then what can we do? We want to solve for the v vector. What do we do? What's that? Do what?
Integrate.
Oh, integrate. I'm sorry, it's wrong of me. So v equals the integral of x inverse f. And then at this point, we need to put in some time dependence, right? So let's say v of t is equal to this, x of t, f of t dt, like that, if you like. Hence, the particular solution would just be x of t times the integral of x inverse of t times f vector of t dt. Now, if we think about that integral as being an indefinite integral, right? That would say that it's like, that would add a constant column. What's the effect of adding a constant column here and multiplying by x? If you allow for the constant to be there, that actually gives us the homogeneous solution, because x times a constant vector c is the homogeneous solution, right? So you could actually, if you think about this integral as being an indefinite integral, you could even erase the p here and say that that's the general solution. Let me write something a little bit more specific. Similarly, we could write r of t is equal to r sub naught plus x of t integral from t naught to t, x inverse of integration variable, let's say u, f of u du. This right here, this solves the initial value problem, dr dt equals to ar plus f, and r of t naught equals to r sub naught. Can you see that it fits that initial data? Like, try it out. If we differentiate, if we plug in time t equals to t naught into my boxed formula, what happens? The integration goes from t naught to t naught, which means the integration is 0, and we're just left with the term before, which is r naught. So we have that r, when we plug in time t equals to t naught, we get r naught. So it fits the data. And the fact that that's a solution follows from what I just went through. If you differentiate that with respect to time, I can do it if you'd like. What happens when we differentiate that with respect to time? What's the derivative of the constant vector r naught? So this is just 0, right? And over here we have a product. We have dx dt times the integral, t naught to t, of x inverse of u, f of u, du, plus x times ddt of the integral from t naught to t of x inverse of u, f of u, du. Which is what? We know dx dt is ax, right? And how about what's the derivative of the integral of the variable bound? We just do what? We plug in the bound, right? Fundamental theorem of calculus part 1, it's often called. So this gives us x inverse of u, not of u anymore, but of t, f of t, all times x of t, right? Notice that okay, so this, what is this piece here? You have ax times the integral. What's the so I shouldn't spend too much time on what we're doing. This piece right here is exactly this times that, right? So if you look at this, we've got a times, r minus r naught. If I haven't made a mistake. And then, on the other hand, what happens over here is you got your x of t and your x inverse of t canceling, and what we're just left with is what? Looks like f. Now, I wanted it to equal to ar plus f. I've got ar plus f. I've got this r naught term. I may be doing well, anyway, I should stop. If we continue on, we'll be able to show that when we plug in the boxed formula into this, we do have that this is equal to that. I'm part of the way there. I'm not quite done yet. But I think it's probably better for me to actually do a specific problem with numbers to continue with the example we already started. So let me invest our time in that rather than finishing this. The boxed equation is true nonetheless. Okay, let's see here. So suppose we want to solve I'll pick something that hopefully won't be too hard for us. We'll see. Suppose we want to solve x, y prime equals to, what was the matrix I already have the fundamental solution matrix for over there? 4, 3, 3, 4, is it? There we go. I'll do that. 50-50, right? Let's see here. And what do you guys think we should make our non-homogeneous term be? See, I'm a glutton for punishment, so no, I was thinking about putting a cosine there. But I feel like if I do that, I'm going to integrate exponentials times cosines. I don't feel like doing that at the moment. Let's do exponentials. Let's say like e to the t, and we'll put a 3 down here. That should be interesting enough. So this is f, so to speak. So we can solve this problem by the method of variation of parameters, okay? And I'm going to solve the problem in the sense of above the boxed equation, all right? So the general solution by the derivation we just went through is r of t equals to x of t, integral of x inverse of t. Goodness gracious. Wowzers. Hopefully I didn't sneeze into the mic. I don't know. All right. Oh, and then what was our x? Well, so if you're doing this problem, is there any point in writing out x explicitly at this point? There is not. You want to leave that as just an x, because you want to do the integration first, all right? Now what's x inverse? We worked that out over there already. So apparently 1/2 e to the t minus e to the t. I'm going to bring the half all the way out front. So e to the t minus e to the t. What's the second row? E to the negative 7t. Do I have it right? All right, I'll put some dividers in because it's hard for me to see it. And then I have to multiply that by my f, which is e to the t and 3. All right, so 1/2 x, the integral, and then I have to multiply my matrices. So I get e to the t times e to the t, which is e to the 2t, minus 3 e to the t, and then I got e to the minus 6t, plus 3 e to the minus 7t dt. Now, let me just write this. Okay, well, let's get to it. I think at this point, it's worth writing out the x. X was, what was it? E to the minus t minus e to the minus t, and e to the 7t, e to the 7t. Was that my x? Was that my x? Did I get the signs right? Okay. Now I need to do this integral. How do you integrate a vector? Do you guys know how to integrate a vector? If I integrate like vector f, well, a bad choice of letters. If I integrate, say, x, y dt, that's equal to integral of x dt, integral of y dt. That's how we do integration component-wise, all right? So in other words, I integrate the top component, I integrate the bottom component separately. How do we integrate e to the 2t? We get a 1/2 e to the 2t minus 3 e to the t plus c1. And next we get minus 1/6 e to the minus 6t minus 1 over 20, minus 3 over 7 e to the minus 7t plus c2. Now, just a little bit of matrix lingo for you. We're looking at the product of a 2 by 2 matrix with a 2 by 1 matrix. This is a column vector, 2 rows, 1 column. This has two rows and 2 columns. So here's a divider. Put a divider in there. That's just decoration. So the multiplication should give us, yet again, a column vector. All right? So let me do it. So what we got here, we've got, if I write down here, can you guys still see it? Okay. Yeah. I don't like to write down there. If you don't mind, I'm going to do something a little bit ugly and write the solution up here. And I'm going to write this, okay, fine. So I'll leave the half out here for the moment. So we have 1/2 e to the t minus 3 plus c1 e to the minus t minus 1/6 e to the t minus 3/7 plus c2 e to the 7t. Let me just try to explain to you guys the calculation I just did there. So I'm just taking the dot product of the column with the row. So this times that gives me these first 3 terms, and this times that gives me these last 3 terms. That's just the definition of column times matrix. It's just the entries are ugly, so it's harder to see. The next component, we have, let's see here, minus 1/2 e to the t plus 3 plus, minus c1 e to the minus t and then minus 1/6 e to the t. What's that? What have I done? I might. Oh, this is I got that plus, didn't I? Oh, it's, yes, thank you. Minus, minus, plus. I do appreciate that. Right, minus, minus, plus. And also, that's a e to the what? Wait a minute.